Welcome back to Engineering Systems. In our previous explainers, we've done some absolutely incredible work getting the FoodDash architecture highly available. We knocked out those single points of failure, we added redundancy, set up automatic failover, the whole shebang. The system is looking remarkably robust right now. But, well, as is literally always the case in engineering, solving one problem perfectly just sets you up for the next one. Today, FoodDash is about to face a totally different kind of challenge. We are dealing with the challenge of success. Okay, let's dive right into this. Imagine FoodDash has suddenly become massively successful. I'm talking thousands of customers opening the app every single minute. Orders are flying in, restaurants are totally slammed, and drivers are constantly accepting deliveries. It's exactly the kind of explosive growth that startups dream about, right? But for our infrastructure, yeah, it's quickly turning into what we like to call a success disaster. Behind the scenes, our poor single application server is just getting absolutely crushed by this massive traffic spike. CPU usage is climbing right to the absolute limit, memory usage is growing completely out of control, and because of all that, response times are tanking. They're getting so slow, and eventually the users start to notice. The app feels sluggish, pages take forever to load, and during the really big spikes, some customer requests just outright fail. Not good.
So, when faced with this kind of severe bottleneck, an engineering team's first instinct is usually pretty straightforward. We just say, let's just buy a bigger server. We call this approach vertical scaling. You upgrade to more CPU, slap in more memory, basically just throw raw, expensive computing power at the problem. And you know what? For a little while, it actually works. The system breathes a sigh of relief, but then FoodDash keeps growing. More users, more data, and inevitably, that single massive server just gets overloaded all over again.
The harsh reality is, you eventually hit a physical wall. You simply cannot scale one machine infinitely forever. There's a literal physical limit to how big a single server can be built. So this is where a major architectural pivot has to happen. Instead of trying to buy a bigger server, the team decides to pivot towards buying more servers. They make the call to distribute the workload.
To actually do this, FoodDash launches an entirely new architecture. Instead of one giant struggling machine, we spin up 3 distinct application servers. Let's call them Server A, Server B, and Server C. Okay, so now we've got 3 separate machines ready to share the heavy lifting. At first glance, boom, bottleneck solved, right? Well, by doing this, we've immediately introduced a brand new, highly complex puzzle into the system.
Think about this for a second. When a super hungry customer opens the FoodDash app on their phone and hits order, which server actually gets that request? Is it Server A, Server B, maybe Server C? How do we possibly decide? We have all the computing power we need now, but we completely lack direction.
You see, every single request that hits the front door of FoodDash needs a specific destination. Something has to make the decision about where that traffic goes. Without a system actively making that routing decision, our shiny new multiple server setup literally doesn't know what to do. It's kind of like having 3 completely empty checkout lanes at a grocery store, but no sign telling customers which one to line up in. It's just chaos.
And this is exactly where the load balancer enters the picture. The load balancer is such an elegant solution to our routing dilemma. It essentially acts as the new, intelligent front door for all FoodDash traffic. Think of it as a highly efficient traffic controller. It sits right in front of your fleet of application servers, intercepts every single incoming request from your users, and then smoothly distributes those requests across your backend servers. And this brilliantly illustrates the power of that setup. Let's say FoodDash gets a massive spike, where 300 requests hit all at the exact same moment. Without a load balancer, one unlucky server might catch all 300, get totally overwhelmed, and just crash. But with the load balancer, it neatly splits the block. 100 requests go to Server A, 100 to Server B, and 100 to Server C. Each server handles a totally manageable workload, and the whole system stays lightning fast. This is what engineers mean when they talk about horizontal scaling. You scale out by adding more machines, rather than scaling up by making one machine bigger. And the absolute key takeaway here is that horizontal scaling is genuinely only possible with a load balancer. Without it, having a massive fleet of servers is basically useless, because the raw internet traffic still needs a reliable way to actually reach them.
So naturally, this brings up another really fascinating question. If the load balancer is our master traffic controller, how exactly does it make the decision on where to send each individual request? Well, there are actually a ton of different strategies and algorithms it can use. It's a huge topic. But just to get the basic intuition down, let's look at the absolute simplest one available.
It's called the round-robin algorithm. And honestly, it works exactly the way it sounds. The first request comes in, goes to Server A. The very next request, handed to Server B. The third request goes to Server C. And then it just repeats the cycle from the top. A, B, C, A, B, C. It's incredibly simple, it's perfectly predictable, and honestly, it's surprisingly effective for a vast majority of basic workloads. But here's the thing, modern load balancers do so much more than just blindly distribute traffic in a loop. They actually play a massive role in your system's overall availability. If you recall from our earlier explainer on failover, we talked about health checks. Well, we can actually integrate those vital health checks directly into the load balancer itself. It constantly whispers to every single backend server, continuously checking, hey, are you healthy? Are you ready to receive traffic?
Let's walk through a live failure scenario to see how cool this actually is. Say disaster strikes and server B suddenly crashes because of a bug. Because of those continuous health checks, the load balancer detects the failure almost instantly. It realizes, uh-oh, server B has gone dark. So it automatically stops sending traffic to the dead server and seamlessly reroutes all new incoming requests exclusively to server A and server C. The users ordering their lunch, they never even notice a crash occurred. No way.
This is just a beautiful synthesis of the system design concepts we've been covering. Health checks provide the vital intelligence by identifying the dead servers. Then the load balancer acts on that intelligence to make real-time routing decisions. Together, they create this incredible system of automatic traffic rerouting that cleanly bypasses failures without any human intervention whatsoever. It is absolutely crucial for making a distributed system truly resilient.
But wait, let's flip the script for a second here. We've just routed all of our vital incoming internet traffic through this one amazing device. So the really uncomfortable question we have to ask ourselves now is, what happens if the load balancer itself fails? If the load balancer goes down, literally nobody can reach the application servers sitting behind it, even if all 3 of those backend servers are perfectly healthy and just sitting there waiting for work.
Yep. By trying to solve our scaling problem, we have accidentally introduced a brand new single point of failure, or SPOF, right at our front door. As we know, an SPOF is any component that can bring down the entire system if it fails. The load balancer is an amazing tool, but if we only have one sitting there, that is a massive vulnerability just waiting to cause a major outage.
Now, if you've been following our engineering journey, you probably know exactly how we solve this. Just like we duplicated our backend servers, we absolutely cannot rely on just one load balancer. We have to move from a single point of failure model to a highly available model, and we do that by deploying redundant load balancers. If the primary load balancer goes up in smoke, a fully synchronized backup is sitting right there, ready to instantly take over the traffic directing duties.
Whew, okay, let's take a quick breath and recap this incredible evolutionary arc our architecture just went through. FoodDash completely outgrew its single server. To fix it, we added multiple servers to handle the load. That created a routing nightmare, so we brought in load balancers to distribute the traffic. We then integrated health checks so the load balancer could intelligently avoid crashed servers, and finally, we deployed redundancy at the load balancer level so we wouldn't have a single point of failure at the front door.
We've built a seriously resilient, scalable system today, but honestly, we've really only scratched the surface of how the load balancer makes those routing decisions. Round robin is great and all, but what if server A is physically more powerful than server B? What if server C is already totally bogged down with a really complex query? Or what if one server just inherently responds faster than the rest? Should they all really get the exact same amount of traffic? These are fascinating, complex questions that require much more advanced algorithms, and that is exactly what we are going to unpack in our next explainer. Thanks for hanging out with me, and I'll see you next time as we continue building great systems.